I'm going to be talking about spatial light modulators and mode division multiplexing. I think spatial light modulators, SLMs, have a lot to offer MDM research, particularly as characterization devices. And I know several groups have already started using SLMs, and some groups are looking to use SLMs for the first time in the future. So I thought it would be useful in this talk not just to mention some of the different characterizations you can perform using an SLM, but also I thought it would be useful to talk about some of the effects you have to be aware of when working with an SLM in the lab, particularly for the first time. You probably already know what an SLM is, but in case you don't, it's very similar to a liquid crystal display in that both consist of an array of liquid crystal pixels. But whereas for a display you're interested in some sort of intensity pattern programmed onto the surface of the display, for an SLM you're interested in programming some sort of phase distribution onto that panel. But what you're really interested in is the Fourier transform of that phase distribution, because your fiber sits in the Fourier plane of the SLM, and that's where you want to excite the desired mode. There are several different liquid crystal technologies around. The two most common are pneumatic and ferroelectric liquid crystals. The pneumatic liquid crystals offer grayscale modulation. They're the same type used in most computer displays. It's possible to do many different phase levels with this type at video-like frame rates of tens of hertz. Pneumatics act on polarization as a variable retarder, where one polarization sees no change and the other polarization sees a phase shift. Ferroelectric liquid crystals work in a slightly different way. They have binary modulation, only two phase states, 0 or pi, but they have kilohertz refresh rates, and they act on polarization as switchable wave plates. Each pixel is like a little wave plate you can program at two different orientations. However, the pixels must spend an equal amount of time in each of their two states, or the liquid crystals will decompose over time, which makes refreshing the SLM more complicated, but you can get around it. Some SLMs at least were originally designed as micro displays and are now being used as SLMs. And as you may know, many displays have a flicker to them as they refresh. The pattern on the display might fluctuate at the refresh rate of the monitor, and for a display, obviously that's not a problem as long as it's happening too fast for your eye to see. But for an SLM, it can be problematic, not just because we're working on timescales which are much shorter in telecoms, but also because we're working in the Fourier plane rather than the plane of the SLM itself. Here we've got a blaze grating, which should create a single spot, the first diffractive order, but there's some very slight fluctuations going on in the plane of the SLM, and that's manifesting itself in the Fourier plane as other diffractive orders, such as the 0 order, 2nd order, and the -1 order. Christoph Bay, a PhD student, since graduated from our group, has put photodiodes at those locations, and here he's measured the fluctuations in the power are occurring at about 300 hertz, which is the refresh rate of the SLM. Which brings us to the 0th order of diffraction. In theory, there should be no 0 order of diffraction. It should be completely suppressed. But in practice, you're going to get at least some small proportion of your power arriving at the center of the Fourier plane as the Fourier transform of your input beam, regardless of what you program onto the surface of your SLM. This can be due to things like flicker and phase noise, as I just mentioned, but it can also be due to things like the finite extinction ratio of your polarizers, reflections such as off the surface of the cover glass on your SLM, or maybe other lenses, beam splitters, fiber facets, etc. There's a lot of different things that can give rise to stray light traveling down the optic axis. And if you've got a weak Gaussian there, then obviously that's going to limit your modal extinction ratio, as you'll always be exciting a small proportion of LP0X modes. So what I tend to do is I always generate my modes slightly off axis, just enough to avoid the 0 order spot. The other thing to be aware of is that the surface of your SLM might not be perfectly flat. Here's an interferogram of the surface of an SLM, and you can see from those fringes that it's not perfectly flat, it kind of bulges in the middle. So you're going to have that phase bulge superimposed on any phase pattern you program onto the surface of your SLM. And that's going to be an aberration in your system, and it could limit your modal extinction ratio. It also means your extinction ratio might vary depending on where on the SLM you place your mask, depending on how flat that portion of the SLM happens to be. But if you know what that surface flatness profile is, you can apply the conjugate to all your masks and cancel that out. Now for the actual experiments you can do using an SLM, you can use an SLM in place of a fixed phase plate etched on glass. But because an SLM generally works as a reflective rather than a transmissive device, and because it's polarization sensitive, the optics you need to work with it are more complicated, as you can see by the system on the left versus the one on the right. However, there's still reasons you might want to use an SLM over a fixed mask, particularly in a laboratory setting. It's good for prototyping, so you can try many different phase masks very quickly and then decide which ones you actually want to bother to get etched on glass. From a practical standpoint, it's also useful. So for instance, here's my reconfigurable mode demux, which I'll be talking more about on Thursday. You don't have to know too much about how it works just yet. You can just see there's two polarizing beam splitters and two mirrors, and they have to be accurately aligned and stuck into the metalwork such that they can hit the 10 micron output fiber. Now obviously that's very precise work, and for precise work you need precise tools, and that's why I use the following items for alignment. You've got blue tack, of course, toothpicks, and my bare hands. You won't find any of those items in the Newport or Thor Labs catalogs, and that's because they have no place in optical alignment. But luckily, because the SLM is a dynamic system, it can compensate for your incompetence, and here it is adjusting the tilt of a blaze grating to find the position of the output fibers on the two different optical paths, the two different polarizations. And you can see that those two gratings look very similar, but they're not exactly the same, and that difference between them corresponds with the fact that the PBS and the mirrors aren't exactly at 90 degrees. It can also do other nice things, like find the center of the beam for you, or find the aberrations in the system for you. That'll improve your insertion loss, but it'll also improve your modal extinction ratio. As for the actual experiments, I'll be talking more about this on Thursday, but I'll mention it here briefly. Here's an example where I've launched each mode of the fiber one at a time and measured its impulse response. And from that you can get the group delay of each mode, but you can also sweep the wavelength of the laser and measure how the group delay changes with wavelength. You get the, i.e. the chromatic dispersion of each mode. And you can use that to infer what the doping profile of that fiber is, if you already have a rough idea what that could be. The other thing I'll be talking more about on Thursday is how you can use an SLM at both ends to launch each mode one at a time at the transmitter and decompose the beam arriving at the receiver in terms of full amplitude, phase, and polarization, and track how that evolves with time. I'll talk more about that on Thursday. Thanks for listening.